Exponential functions. Exponential functions are characterized by variable exponents. They model situations that exhibit exponential growth, like a rabbit population doubling every 6 weeks, or exponential decay, like the half-life of chemical compounds. The basic form of these functions is f of x equals b to the power of x. So you see that the exponent is a variable. If the exponent is positive, like y equals positive 2 to the power of x, then the function is increasing, which is exponential growth. If the exponent is negative, like y equals 2 to the negative x, then the function is decreasing, which is exponential decay. So in your homework, you're asked to graph by making a table of values, and so that everybody has the same thing, in our table, under the x column, we're always going to use -2, -1, 0, 1, and 2. And then the function goes in the middle, and then one at a time, you're going to plug the x values in for the x, and you can put that into your calculator. So when we put in the -2, we get 1.8, -1 gives us 2.3, and so on. Then we have 5 points to plot. The first one is at -2, 1.8. Then -1, 2.3. 0, 3. 1, 3.9. And 2, 5.1. And then connect the dots, and the graph should be curving up. The exponent is positive, so we have exponential growth. Some of the y values on your homework are large, so you might want to adjust the scale for your graph, like count by 5s or 8s or 10s. Just make sure you mark that on the graph itself so I know what your scale is. With population growth and decay, we use the following form of the exponential function, and it's p of t equals p naught b to the power of t. The little 0 subscript is read naught, like nothing. And anytime you see a variable in a formula with that little 0 subscript, that always means a starting amount. So p of t is the population at time t. P naught is the starting population. B stands for the growth or decay rate. And then T is time. If the population is doubling during a specific time formula, then the formula becomes P of T equals P naught times 2 to the T, because the growth rate is doubling. Sample of a doubling population. A bacteria culture contains 1,500 bacteria initially and doubles every hour. Part A, find a function n that models the number of bacteria after t hours. So we'll use that doubling population formula from the previous screen. And we don't know t, they just want us to fill in the letter t. The initial population is 1,500, and it's times 2. And again, we don't know t, so to the power of t. So that's just the general form for this particular situation. Part B, find the number of bacteria after 24 hours. So now we have a number to put in for t. So the population after 24 hours is 1,500 times 2 to the power of 24. I want to caution you about remembering the order of operations. You would not do 1,500 times 2 and then take that value to the 24th power. Remember, exponents come before multiply. Now, in the graphing calculator, when you plug that in, you get 2.5165824 E10. That E stands for scientific notation. So the way you would write the answer is, let's round to 2 places, 2.52 times 10 to the 10th. Exponential growth also affects interest problems. So here's a formula for compound interest. A of t equals p times 1 plus r over n, all to the power of n times t. And so I've given you a list here of what everything stands for. A of t is the amount of money we have after t years, and that would include our initial investment plus the interest. P stands for principal. That's the starting amount, the amount you've invested. R is the interest rate, and the percent has to be converted to a decimal, and so you move the decimal 2 places to the left. Sorry, some of that got chopped off. N is the number of times per year the interest is compounded. So if it's weekly, that's the part that got chopped off. If it's weekly, for example, that means N would be 52 because there's 52 weeks in a year. If it was monthly, N would be 12. And then T is the number of years. So let's practice one of those problems. If $500 is invested at an interest rate of 3.75% per year, compounded quarterly, find the value of the investment after a given number of years. And so we have to do it 3 times, and I've written down from the formula what all of the little parts should be. And again, here's the formula. So we've got that P is $500. That's the amount invested. The rate is 3.75%, but remember you have to move the decimal 2 places to the left, so 0.0375. N is the number of times the interest is compounded per year. So if it's quarterly, that's 4 times a year. N would be 4. So we have everything to fill the formula in except for the year. So I did that just to save us a little bit of time. And now we want to do 1 year, 2 years, and 10 years. So part A, we fill a 1 in for the T, plug all that in the calculator, and we get $519.02. Part B was 2 years, so we fill a 2 into the for T into the calculator, $538.75. I don't know why there's a double dollar sign there. And then part C, after 10 years, we fill a 10 in for T into the calculator, 726.23. Just a graphing calculator note, if you press second enter on the graphing calculator, it will call up your last entry. If you do it again, it'll call up the entry before that. So it'll do a few previous entries. That's handy for problems like this where the only thing that changes is this one little number up here. So you can put it in the first time and then do second enter, call it back up, and just go change the time value and not have to re-enter all of that stuff again.